Okay, hello guys. Today we are in the QMexico webinar, and today we have a very good speaker. This he's Pawl Gora. He's talking from Poland, and his talk is about the an introduction about the quantum computing. Okay, hello guys. Sorry, Andrea.
Hello.
Okay, today we have two coordinators from QMexico. The other one is Andrea. Andrea, do you want add something about the talk today that we are going today?
I think you've mentioned everything. I guess the only um, last thing that we should mention is that we're switching our title for the webinars from just Q Mexico webinars to Q Talk to stay in tune with people.
Sure. Okay, so Powell, how are you,
Yes,
Powell?
yes,
How are
yes,
you,
yes. I'm
Powell?
here. I'm fine. I'm ready.
Nice. So, do you want to start now, or yeah,
Yeah, sure. We can start.
yeah? Go ahead, please.
Okay. Thank you very much. Thank you, Javier. Thank you, Andrea. Thanks for the introduction. Thanks for having me here. It's a pleasure for me to take this opportunity to give a talk about introduction to quantum computing for people, for a community of QMexico. My name is Pavel Gora. As you can see from my slide, I'm a founder and CEO of the Quantum AI Foundation. I will tell a bit more about the foundation on the next slide, but maybe I will also mention that I'm also a member of the board of QWorld and Q Poland. So Q Poland is a Q cousin of Q Mexico. So we are similar groups operating under the QWorld umbrella. And I'm also a leader of the Warsaw Quantum Computing Group meetup, which is, I guess, a very similar series of meetups, webinars, but in Warsaw, in Poland. All right, so before I start talking about quantum computing, I will also tell you just a few words about the Quantum AI Foundation. We established this foundation in 2019, and as you can see, we are a charity organization aiming to support development and collaboration in science and new technologies, especially artificial intelligence and quantum computing, but also other fields of mathematics, computer science, and physics. And as I said, we organize Warsaw Quantum Computing Group meetups and quantum computing workshops of Q Poland. So I guess that I hope that we'll have some opportunities to discuss and to tell a bit more about Q Poland and Q World in the later part of this lecture, because I'm planning first to give you just an introduction to quantum computing, to give you a bit or a qubit of theory, and later I'm going to tell you about some possible applications of quantum computers. Hopefully, if we have time, I will also introduce you to the ecosystem of quantum computing and how we build this quantum computing ecosystem without a QWorld together with QMexico. And hopefully, we'll have some time for your questions and my answers to your questions. So let's start. What's the quantum computing? So the simple answer is that these are the computations according to the laws of quantum mechanics. So I guess that some of you might have already heard about quantum mechanics, but what does the word quantum actually mean? So in physics, a quantum is the minimum amount of any physical entity, a physical property, involved in an interaction. And the fundamental notion that a physical property can be quantized is referred to as the hypothesis of quantization. And this means that the magnitude of the physical property can take only on discrete values consisting of integer multiples of one quantum. And it has some interesting consequences because so we live in a physical world. So computation is a physical process. So it's governed by the rules of the physical world, which is inherently quantum. It's governed underneath by the rules of quantum mechanics. So of course we can talk about the algorithms, some mathematical models, but at the end our computations are run on physical systems, physical hardware, which is governed by the rules of physical world and quantum mechanics. And it has some interesting consequences. I guess that the beginning of quantum mechanics is at least the end of 19th century, and Max Planck's postulate that the electromagnetic energy could be emitted only in quantized form. So the energy might be proportional to the frequency of a photon, and there is a constant called Planck's constant, which just describes this relationship between the energy and the frequency of a photon. So this is just an example that the physical property of energy can be emitted in quantized form. But there's also famous Landauer principle, which basically says that there is a minimum possible amount of energy required to any logically irreversible manipulation of information. For example, erase one bit of information. And you can see that there is also a Boltzmann's constant involved, and there is a temperature of the environment involved. Yeah, there is this minimum possible amount of energy. So if we do computations, we cannot run computations with as small amount of energy as we want. There is a minimum. So we can see that there are some constraints related to our physical world. The famous physicist Richard Feynman, in his book There's Plenty of Room at the Bottom, said that there's nothing that I can see in the physical laws that says the computer elements cannot be made enormously smaller than they are now. And in fact, there may be certain advantages. I also guess that some of you have heard about the Gordon-Moore's law, which says that the number of transistors in a dense integrated circuit doubles about every 2 years. So it seems that we are going toward this imagination given by Richard Feynman that computer elements can be made smaller and smaller, because it turned out that this Moore's prediction proved accurate for several decades and has been used in the semiconductor industry to guide long-term planning and to set targets for research and development. But in 2015, even the Gordon Moore himself says that I see Moore's law dying here in the next decade or so. Intel, a large company working on computer processors, also in 2015 realized that the pace of advancement has slowed. So this doubling of the density of integrated circuit is now not once per 2 years, but once per 2.5 years. But 2 years later, they said that the trend will continue thanks to the invention called hyperscaling. But anyway, can it continue forever? Probably not, because if the Gordon-Moore law has to be continued for 10, 20, or 30 more years, then in about 2035 or 2040, a size of a single transistor should be of the size of a single atom. And then the transistor will be governed by the rules of quantum mechanics. So we should think about some other models of computations which takes quantum mechanics into account. The same scientist, Richard Feynman, 20 years later said that now we can in principle make a computing device in which the numbers are represented by a row of atoms, with each atom in either of the two states. That's our input. The Hamiltonian starts Hamiltonianizing the wave function. The ones move around, the zeros move around. Finally, along a particular bunch of atoms, ones and zeros, occur that represent the answer. Nothing could be made smaller. Nothing could be more elegant. No losses, no uncertainties, no averaging. But can we do it? And that's the question. And since we are now talking about quantum computers and quantum computing, I guess that you already know that the answer is positive, or at least seems to be positive, because we can already build some relatively small and still very noisy quantum computers, but there are some interesting advancements in the recent years. So here in these graphics, you can see to the left a Bristicle, which is a quantum processor developed by Google, and on the right is a cartoon of this device where each X represents a qubit with nearest neighbor connectivity. So this is just an example of a model of quantum computer, but as you probably know, there are many more ideas how to build quantum computers nowadays. All right, so what is exactly quantum computing? It's computing according to laws of quantum mechanics. What are the differences between classical computers and quantum computers? So in case of classical computers, we have bits and classical gates. So here you can see some examples of classical gates, AND, OR, NOT, XOR. So these are just standard classical gates. We just take some bits. So bits may take values 0 or 1, and these classical gates can just take the value 0 or 1 as an input, and then they can do some transformations and give an output, which may be again an input to the next classical logical gate. So as I said, in case of classical computers, the bit may have a state which has a value 0 or 1. So mathematically, it's something very simple. It's just an element from the set 0, 1. But in case of quantum computers, we have qubits. And in case of qubits, the state may be a superposition of states 0 and 1. So what is this superposition? So as for now, you can think that this is something in between 0 and 1, but it's not just 0.5, for example, right? Because this is something much more complicated, or even we can say that it's more complex, because here we'll have to deal with complex numbers. So mathematically, the quantum state is a unitary vector of the two-dimensional Hilbert space over complex numbers. So it sounds quite, it may sound quite difficult or complicated, but later I will show you how to think about quantum states in a more intuitive way. So another difference is that in case of classical computers, the state is determined. So in any time, we know exactly whether the state is 0 or 1, and we can just check it. We can do a measurement, and we can change the state from 0 to 1 and vice versa. So it's relatively simple. But in case of quantum computers, we have this superposition of states 0 and 1. So in order to get values 0 or 1, we have to do a measurement which breaks superposition. So we just have a probability of getting 0 or 1 after the measurements. And this probability just depends on the qubit, which is this unitary vector of the two-dimensional Hilbert space over complex numbers. And our quantum gates can just modify qubits, and they can just modify the probability of getting 0 or 1 after the measurement. So later I will tell you a bit more about quantum gates, but now let's try to describe what exactly is this qubit and quantum state and quantum superposition in maybe a bit more intuitive way. So here you can see just a description of a quantum state where 0 and 1 are our pure states. So we can say that they are orthonormal base of a quantum system. So you remember that we have this two-dimensional Hilbert space. So the 0 and 1 are just pure states or orthonormal base of our quantum system. And A and B are complex numbers, such that the squares of their amplitudes are probabilities of getting 0 or 1 in a measurement. So the sum of these squares of amplitudes should be equal to 1. And now, from a property of complex numbers, we know that by multiplying these complex numbers A and B by a unitary vector, complex, unitary complex number, it doesn't change the quantum state. So A and B can be transformed to spherical coordinates. This is the representation of another representation of the space of quantum states, which is called a Bloch sphere. So at the bottom of this slide, you have the transformation or another representation of a quantum state in which we don't have the complex numbers A and B, but instead we have two angles, theta and phi, right? And we can see that there are similar angles on our Bloch sphere. And this is just a simple exercise to just show that any quantum state for any arbitrary complex numbers A and B, such that their sum of their amplitudes is equal to 1, we can just make such a transformation that the coefficient with assigned to 0 is just a cosinus of one angle, and another the coefficient assigned to this unitary vector 1 is represented as e to the power I phi and another trigonometric function of an angle. So what is important here? Because these are just some mathematical formulations and simple mathematical exercises. But a good intuition is that a quantum state can be represented as a point on this block sphere, where this point is just determined by two angles between a lane determined by a given point on a block sphere and two axes in this block sphere, right? So we can say that, so in case of classical computers, bits or states of bits can be just 0 or 1, so they are just antipodes. These are just only 2 points on this block sphere. But in case of quantum computers, the qubit state can be any point on the block sphere. And that's why sometimes we say that quantum computing is just a journey on a block sphere, because applying quantum gates to our quantum states, to our point, just transform quantum states to another points on this block sphere, right? And now I will just give some examples of notable quantum gates which just make such transformations. So, for example, we may have the Hadamard's gate, which transform this pure state 0 and 1 into superposition of state 0 and 1. We have the Pauli gate, which we can think that this is just a correspondence to the negation, because 0, the pure state 0 is transformed to pure state 1 is transformed to pure state 0, etc. And similarly, we have Pauli Y gate, Pauli Z gate. These are just 1 qubit gates, so they just take just a single qubit as an input and just make transformations. But there might be also quantum gates with which take 2 qubits as an input. So the CNOT gate is a notable example, because in a CNOT gate, 1 qubit is a controller for applying the NOT, so this X Pauli gate on the second qubit. Right, and an interesting thing is that any quantum circuit, any quantum computation can be simulated to an arbitrary degree of accuracy using a combination of CNOT gates and single qubit rotations. So these X, Y, Z Pauli gates are just single qubit rotations. So I will just show you how we can think about them as rotations. So this is just the Hadamard's gate, and I explained that this gate may just transform pure state 0 and 1 into superposition of state 0 and 1. So to the right, you have a graphical representation of this Hadamard gate. And we can also say, and we can also realize that this Hadamard's gate represents a rotation of p degrees, so 180 degrees, about the axis x plus z. So we had this x and z axis on our block sphere. So we can think about rotation of 180 degrees about an axis determined by axis x and z. So alternatively, we can also say that this is p over 2 rotation around y-axis, and then a rotation by 180 degrees around z-axis. And here we can also see a matrix representation, because we operate in a Hilbert space, so we operate on vectors. So pure state 0 and 1 has also a vector representation in this 2-dimensional Hilbert space. So for any such a rotation, for any such operation, we also have corresponding matrices. So this is just a matrix representing the Hadamard's gate. Similarly, this is a matrix X representing the X Pauli gate. And it represents a rotation of p about the axis x. So that's why it's called X Pauli. CNOT gate. So this is this interesting gate with which takes 2 qubits as an input. So CNOT acts on 2 qubits and performs the NOT operation on the second qubit only when the first qubit is 1, and otherwise it leaves it unchanged. And here you can also see the CNOT matrix representation of the CNOT gate. All right, and by using such gates, we can build more and more complex quantum circuits. So here is just an example. So let's assume that we just takes as an input n pure states 0. So we have n qubits, and each qubit is transformed first using the Hadamard's gate. So we have a superposition, right? So 0 is transformed to a superposition of states 0 and 1. And after that, after this superposition, we can say that our quantum state can represent all of the possible 2 to the power of n numbers, right? So if we do a measurement after just performing these Hadamard gates operations, each of the 2 to the power of n numbers represented on n qubits will be equally probable as an outcome, as an output, right? So thanks to that, on n qubits, we can represent 2 to the power of n numbers, right? And then we can just apply some other quantum circuits. So here they are represented as a quantum circuit U. We can apply these quantum operations, another set of quantum gates, and we just do computations on all of these quantum states at the same time. And after the measurement, we can get some output, right? So our quantum gates, when we apply quantum gates to our quantum states, we just modify the probabilities of getting zeros or ones after the measurements. So here is an example, relatively simple example of computations performed this way. So initially, we just give as an input to this quantum circuit 8 qubits, which initially are just in a pure state 0. And as we can see, in case of qubits number 3, 5, and 7, we don't apply any quantum gate, right? So after the measurement, the outcome will be still 0. With probability 1, we'll get 0. But, for example, we have a qubit number 6, where we apply the X Pauli gate, right? So again, with probability 1, we'll get the value 1 after the measurement, right? Because initially it was 0 with probability 1. So after applying the X Pauli gate, we'll get value 1 at the end, at the measurement, right? So qubits number 0, 1, 2, and 4 are more complex, because in case of qubit 4, we first apply the Hadamard's gate. So we do, so we have a superposition of states 0 and 1, and states 0 and 1 are equally probable. And then we apply the X Pauli gate, so 0 becomes 1 and 1 becomes 0. And then we have 3 C-node gates. So if the qubit number 4 is 1 or would be 1 after the measurement, then in case of qubit 0, 1, and 2, the C-node gate will be triggered, and the outcome of the measurement should be also 1 here, right? But then in case of qubit 4, we apply the X Pauli gate once again, and the value 1 will be transformed to value 0, and vice versa, right? So we can run such computations, and we'll see that with probability 0.5, we'll receive the outcome which composed of bits 0, 1, 0, 1, 0, 0, 0, 0, which is an ASCII code representation of the letter character upper P. And with the same probability, we'll get an ASCII code representation of the letter G. And these are just initials of my first and last name. So I can say that I just built a quantum circuit that can calculate the ASCII code representation of my initials, right? So this is just a simple example how these computations using such quantum gates and quantum circuits may look like. Later, I will also tell you about another model of computations, but this is just an example. So what are some other differences between classical and quantum computer, and why it is important? So we have seen that in case of classical computers, on n bits we can represent and process only one n bit number at the same time. But in case of quantum computers, using n qubits, we can process all 2 to the power of n n-bit numbers at the same time. In case of classical computers, results are deterministic, and randomness is in fact only a pseudo-randomness generated by our computer. But in case of quantum computers, we may have real randomness, and the advantage is that we can easily sample from probability distributions which might be difficult for classical computers. And this was used, for example, to prove this quantum supremacy. They're quite recent result from 2019. All right, so this was just an introduction to quantum computing. So I hope I gave you a bit of theory. And later I will show you where you can learn more if you are interested. But now I will tell you a bit about some possible applications of quantum computers, because I believe that for many of you it might be also very interesting. So these are just some possible applications of quantum computers. For example, quantum cryptography, breaking some classical cryptography algorithms. So I will show you an example of such an algorithm in one of the next slides. Solving combinatorial optimization problems which frequently occur in artificial intelligence, machine learning, finance, transport, logistics. So in fact, almost all mathematical problems can be somehow transformed to optimization problems. Maybe not always combinatorial optimization, but when we do computations on our computers, we represent all numbers as discrete numbers, zeros and ones. So everything is just a combinatorial optimization, in fact. So it looks that might be very powerful application of quantum computers in the future. Sampling from difficult distributions. So the Boltzmann distribution is just a notable example because it may have some applications in machine learning, and as far as I know, it's difficult to sample from the Boltzmann distribution in case of classical computers. Simulating quantum processes. So this may find application in for discovering new materials, new drugs. Right. So let's now tell a bit more about this quantum cryptography and breaking classical cryptography algorithms. Apparently, it turned out that many of the existing cryptographic algorithms are based on the assumption that factorization of large numbers is difficult for classical computers. So when we want to multiply two n-digit numbers, then we can do that in n log n operations, more or less. So in September 2019, it was proven that it can be done in n log n. You can easily do that in n square if you want, of course, right? But now when we have an n-digit number and we want to factorize it, so we want to find two large numbers, prime numbers, such that when we multiply these numbers, then we get our n-digit number at the end. Then it turns out that this problem is difficult, or it looks that this is difficult, because no algorithm has been published that can factor all integers in polynomial time. So in time that would be upper bounded by a polynomial which is a function of the number of digits and some constant, right? So we don't know any such algorithm, but neither the existence or non-existence of such algorithms has been proved. But it's generally suspected that they do not exist, and hence that the problem is not in class of problems that can be solved on classical computers in polynomial time. So probably the best possible algorithm, that at least deterministic algorithm, will be an exponential algorithm, but it hasn't been proven yet. Best published asymptotic time algorithm is based on general number field sieve, and you can see this time complexity. So you can check that it cannot be upper bounded by a polynomial of n. It's an exponential function of n. All right, but it turns out that in case of quantum computers, we can factorize such n-digit numbers in polynomial time, and there is a famous Shor's factorization algorithm. You can see the time complexity of this algorithm, and this is just a quantum circuit representing the computations. So this is just there is a quantum subroutine because the algorithm is a hybrid algorithm. So there is a classical part and there is a quantum part, and this quantum part is responsible for finding a period of a long sequence using the inverse quantum Fourier transform. So you can see the block representing this inverse quantum Fourier transform here on the right of this quantum circuit, right? So we know that it can be done in polynomial time on quantum computers, and I also heard that there are already some algorithms which are even better than Shor's algorithm in case of quantum computers, of course. I also mentioned about solving combinatorial optimization problems. So these are the class of problems in which we search for the best of many possible combinations. So the examples are some scheduling challenges such as, should I ship this package on this track or the next one? Or what's the most efficient route a traveling salesperson should take to visit different cities? So this is the famous traveling salesman problem. And these problems are usually NP-hard. So they are usually very difficult for classical computers. But it turns out that physics can help solve these sorts of problems because we can frame them as energy minimization problems. And the fundamental rule of physics is that everything tends to seek a minimum energy state. So objects slide down hills, hot things cool down over time, right? And this behavior seems to be universal in our world, also in the quantum world. And there is a process called quantum annealing, which uses quantum physics to find low energy states of a problem and therefore the optimal or near optimal combination of elements. So now I will tell you a bit more about this quantum annealing and adiabatic quantum computers. Just an introduction, an adiabatic process is a process that does not involve the transfer of heat or matter into or out of a thermodynamic system. And in an adiabatic process, the energy is transferred to the surroundings only as work. And there is an idea to build adiabatic quantum computers, so quantum computers which just don't involve the transfer of heat or matter into or out of a system. So the idea is as follows. First, a potentially complicated Hamiltonian is found whose ground state, the state with a minimum energy, describes the solution to the problem of interest. And next, a system with a simple Hamiltonian is prepared and initialized to the ground state. Finally, the simple Hamiltonian is adiabatically evolved to the desired complicated Hamiltonian. So later I will tell you what exactly Hamiltonian is. I guess that many of you already know that. And by the adiabatic theorem, the system remains during this adiabatic evolution in the ground state. So at the end, the state of the system describes the solution to the problem, right? And the interesting thing is that the adiabatic quantum computing has been shown to be polynomially equivalent to conventional quantum computing in the circuit model. So in the circuit model which I presented in the previous slides, right? And there is a papers where it was proven, so that we can polynomially transform one system of computation into another system, which is also very interesting, I guess, at least in theory, because in practice it might be very difficult, of course. So I mentioned something about Hamiltonian. So a classical Hamiltonian is a mathematical description of some physical system in terms of its energies. So we can input any particular state of the system, so for example, a quantum state, and the Hamiltonian returns the energy for that state. And for most non-convex Hamiltonians, finding the minimum energy state is also an NP-hard problem that classical computers cannot solve efficiently. But maybe quantum computers can solve it, right? And this is the idea behind these adiabatic computations, right? So we have, as you can see, we have two Hamiltonians. The one is an initial Hamiltonian, which should be a relatively simple Hamiltonian, right? Easy to prepare, and the ground state of this Hamiltonian, the state of the lowest energy of the minimum of this function, should be easy to find, right? So for example, this can be, so the lowest energy state of this Hamiltonian may be when all qubits are in a superposition of state 0 and 1, right? This is also called the tunneling Hamiltonian. And we may also have another half Hamiltonian, which is a final Hamiltonian, such that the lowest energy state is the answer to our optimization problem that we are trying to solve, right? So the final state is a classical state and includes the qubit biases and the couplings between qubits. So these are the biases and the couplings, or at least these are some constants representing biases and couplings between qubits. And this is also called the problem Hamiltonian. And now you can see that we have some functions A and B, which are functions of S. So S is a strength of a magnetic field. And now the idea of such adiabatic computations and quantum annealing is that initially we prepare our quantum state that is easy to prepare, for which we know the lowest energy state, right? So that the value of this function should be 1 and the value of this function should be 0. But then we modify the strength of the magnetic field such that this part, this Hamiltonian, becomes less and less important, and this part becomes more and more important until this value just becomes 0, right? So at the end, we'll have another Hamiltonian, but as we know, initially, our system was in the state of the lowest energy, in the ground state. And when we do this adiabatic computations, then according to this adiabatic theory, the system should remain in the ground state. So at the end, we should also be able to know this ground state of this very complicated Hamiltonian, which will correspond to this optimization solution to our problem, right? But there are some issues with this. So the first issue is, of course, that now the nature can do computations for us, but we should somehow translate our optimization problem into such a complex Hamiltonian, which in many cases might be difficult. And later, when we have this complex Hamiltonian, which should be of a special form, and later I will tell you what's this form, then we should also translate it into a physical device, a physical quantum system, right? And then we have to do such computations and just modify the strength of a magnetic field. And we should do that slow enough. And there are some issues with this slow enough, because if we do it slow enough, then it may turn out that, again, we'll not have any advantage in the computations, right? But if we not do that slow enough, then it may turn out that will not be in the ground state at the end. But anyway, we can be still in a quantum state that might be relatively good, right? Who knows? So maybe we can just run many such computations. We can repeat our computations many times, and after that, maybe we'll be able to achieve a good result, right? So there is a hope, and this idea partially is implemented in a quantum computer or quantum machine, might be the better word, built by D-Wave. So D-Wave is a Canadian company working on such quantum machines and quantum annealing algorithms. So here is a link. I guess that here we also have a link to the website of this D-Wave Systems company. So I encourage you to check it, because there are also some nice explanations on how this model of computing works. But now let's try to answer at least one of these the challenges which I mentioned before, right? So how to transform our representation, quantum representation, Hamiltonian representation into a physical system. So it turns out that there is something like the Ising model. It's a model for magnetism used in statistical mechanism, and our variables +1 and -1, or 1 or 0, may correspond to spin up and spin down, right? So these are just atomic spins or magnetic dipole moments. Yes, so there are some relationships between the spins represented by couplings, which might be correlations or anti-correlations. And our objective function, a Hamiltonian of this system, is expressed as an Ising model as follows, right? So we have some parameters, coefficients corresponding to qubit biases and corresponding to coupling strength between our qubits, right? So we can, if we can transform our optimization problem to such a form, then we can just translate it to the physical device, the physical quantum system on which we can run this quantum annealing or potentially adiabatic computations, if such computations are possible. And at the end, we can just read what's the ground state, the minimum energy state of the final system, right? And now, so again, this is this idea, right? So we have initial Hamiltonian for which the ground state is easy to prepare, so it might be just a superposition. We have the Hamiltonian corresponding to the Ising model, which for which this ground state should be a solution of our optimization problem. And now we should modify the strength of a magnetic field, right? We should do that slow enough to be sure that finally we'll still stay in the ground state. But in practice, at least in these D-waves quantum machines, it's not achievable at the moment, as far as I know. But why does it work, right? So an interesting property, quantum property that is used here is called quantum tunneling. So in fact, as you can see, by controlling the strength of this magnetic field, we just modify the function, right? So initially you have a relatively simple function for which we know the minimum, we know the ground state, and later we achieve very complicated function for which we would like to know the minimum, the ground state, right? And when we continuously modify the strength of the magnetic field, we just modify this function, and we just modify the so-called landscape of this function, right? And now it may turn out that we are currently, when our system was in a state that was a ground state of this quantum system, when we modify the landscape, it's not a ground state anymore. But thanks to this quantum tunneling, we can just jump to another potentially global minimum, a potentially ground state, which will correspond to the later, after all these transformations, will correspond to the minimum of a quantum state of our problem after the end of the computations, after the end of the transformation. So basically, that's the idea, and I encourage you to watch the videos prepared by D-Wave, where there are some nice explanations of this property, and I'm sure that they can explain it much better. All right, but there's another problem which I told you about in this kind of computations, and the problem is that we should somehow transform or translate our optimization problem, our combinatorial optimization problem, to the Hamiltonian of an Ising model, right? And the Hamiltonian of this Ising model, again, corresponds to something that is called the quadratic unconstrained binary optimization problem. So this is the formulation, right? So as you can see, we have some variables, and we may have only the square or the power of 2 of exponents, right? For different for different variables. So that's why this is called the quadratic. This is called also binary because we assume that the values of this variable should be 0 or 1. So these are only binary variables, and we want to find an optimum, a global optimum. That would be best, to find the global optimum of such a function in the binary domain, right? We have some number of binary variables, and we want to find any minimum of this function. And we have some parameters which just correspond to strength of the couplings between qubits or biases, right? And this QUBO formulation, as you can see, we have some coefficients q, and we can just represent it as a multiplication, right? We have vector x and transposed x and a matrix q with our coefficients corresponding to strength of couplings between qubits and to biases, right? And so this is the function that we want to optimize. So now the idea is that we want to transform our optimization problem into such a form as QUBO, right? So that's the idea. So now how to do that? I will show you an example how to do that, because this is very nice application in transportation, in solving some optimization problems in logistics. The experiment was conducted by the researchers from D-Wave and Volkswagen, and this is a paper from 2017. The title is Traffic Flow Optimization Using a Quantum Annular. I encourage you to read it because this is a very nice paper. So initially, these researchers built a road network, and they had real routes from real GPS data. There is a data set called T-Drive. It's a data set of routes of taxis in Beijing, in China. And for each car, so they had some number of cars for which they had routes, real routes. And for each car, they added 2 possible routes between source and destination. So the source was basically the city center, and the destination was the airport in Beijing. And there was an assumption that cars may share road segments, and that the travel time is proportional to the function, which is a square of a number of cars on a route. And this is a simplification, right? Because they just aggregate and count, just sum up all cars passing a given road segment. But of course, different cars may pass a given road segment in different time periods, right? So so it's not necessarily true that that would be the real time of travel of these cars, but this is just a simplification which makes the computations very elegant and very simple. And I will show you why this is simple and elegant, because there's very nice QBO formulation. There's very nice formulation of this quadratic unconstrained binary optimization problems when we do such an assumption. And now our goal is, of course, to minimize the total travel time of all cars, right? So each car has now 3 possible routes to select from. So 1 route which was a real route in the real world, and 2 alternative artificially generated routes. Okay, so let's introduce some notations. So the variable Qij may take values 0 or 1, and it just represents a situation that car I takes route j, and then the value of this variable is equal to 1. Otherwise, so if car I doesn't take route j, then the value should be 0. So we have 3 possible indices here, right? Because for each car, we have 3 possible routes. That's why when we do this summation here, we sum over all possible values of j. We have 3 possible routes, and for each car, exactly 1 route should be selected, right? Exactly 1 route should be selected. So the sum of squares for all cars should be equal to 0, because each sum should be equal to 0, because we should have exactly 1 value 1 for exactly 1 value j for each car I. Yes? And we can transform, you can just do computations, and if we just raise Qij to the power of 2, then because the values are 0 and 1, then this is the same as just Qij, right? So we have this equation. And this is a condition that should be satisfied in order to ensure that each car takes exactly 1 route. So this is a condition that should be fulfilled, right? And then we define the cost function that we want to minimize. So I mentioned that the assumption was that the time of travel on a given road segment is proportional to the square of the number of cars on a given route. Yeah, that was this assumption. Travel time is proportional to the square of a number of cars on a given route. So it's a simplification, but it's reasonable, right? So this is a cost of traveling through the road segment S. And here we just have a set of all variables associated with routes that share this street segment, right? So for all cars which selected the route having the road segment S, we just add a value 1 here. So we just aggregate all cars which just travel through this road segment S sometime in the during the ride, right? So as I said, this is a simplification because we assume that they travel through this road segment at the same time. But anyway, that might be reasonable from one perspective, because anyway, we just have only we have only a sample of the real traffic, right? And we can say that the real number of cars traveling through a given road segment might be proportional to the number of cars from our sample that selected this road segment. So it doesn't have to be true, but this is just a simplification. And then we have an objective function where we just sum all costs for all road segments in our road network. So this is the total cost, and this is something that we want to minimize. We want to minimize the cost of traveling through all the road segments in our network, but then we should also ensure that all cars selected exactly one route, right? So now we should set the value of this parameter lambda large enough to ensure that in any solution of this optimization problem, this component will be equal to 0, because this would imply that each car selected exactly one route, and our condition will be satisfied, right? So the value of parameter lambda should be large enough to ensure that in any solution found by any solvers solving this optimization problem, because this is an optimization problem, this condition will be satisfied, right? And then when we just look at the definition of the cost S and definition of our conditions, then we realize that indeed this is just a quadratic unconstrained binary optimization, because we have some parameters, we have our variables, which are binary variables. They may take values 0 or 1, and the highest exponent here is just the power of 2. So this is a quadratic binary optimization. And we can also build this matrix corresponding to the QBO problem. So this optimization problem, can be translated into an async model and later can be solved using quantum annealing on D-Wave's quantum machine. And indeed, these researchers from D-Wave and Volkswagen conducted such experiments. As I said, they just selected 418 cars. So for each car, we had 3 possible routes. So in total, there were 1,254 logical variables, binary variables. So we can also estimate or calculate what's the number of possible solutions for this optimization problem. So of course, not all solutions are interesting for us, because in some cases, these constraints, the mentioned constraints, will not be satisfied, right? But as a result, so they solved this quadratic unconstrained binary optimization, and as a result, they achieved a relatively small number of streets that were heavily occupied. So here we have 2 figures presenting the traffic density, so number of cars in the real world. So that was a real traffic in Beijing, consisting only of these 14.8 taxis, right? And here is a result, a distribution of routes, distribution of cars in the best solution found by D-Wave's machine. And the time of computations was relatively small, 22 seconds. So on classical computers, will not be able to just explore all the possible solutions in such a time. So of course, this quantum annealing approach enabled running such computations. It's hard to say whether the solution was a global optimum or not. Probably not, most likely not. But anyway, it seems that the found solution was quite realistic. Another question is whether we'll be able to achieve similar results on classical computer. It's quite likely, because there are already some good solvers, heuristics or meta-heuristics approximation algorithms able to solve similar optimization problems. But anyway, it seems that this is quite an impressive achievement for early stage quantum computers. Another application for improving logistics, solving the traveling salesman problem and similar problems, vehicle routing problem, pickup and delivery problem with limited capacities, with time windows. And there are already some quantum algorithms for solving such problems on quantum computers. So we don't have large enough quantum computers yet to get a real advantage, but we already have some interesting algorithms. And there are already some logistic companies interested in such solutions. Some other applications of quantum computing, quantum machine learning, quantum AI. There are many fields where quantum computing may enhance machine learning because, as you may know, machine learning is almost all about optimization. Even if you train neural networks, then in fact you just solve an optimization problem because we want to find a set of values for parameters for weights between different neurons, such that you will receive a minimum loss value of a loss function, or in fact maybe not exactly minimum, but the value or the value of a loss function that would be quite good on a training set and would keep the same property on a validation and test set, right? But anyway, this is an optimization problem which currently on classical computers is solved using gradient descent and the backpropagation algorithm. Quantum sampling. So as I said, we can in quantum computers we can sample easier from some difficult distributions. Manipulating matrices. So again, in the machine learning, in AI, we deal a lot with matrices and tensors. Even computations such as inversing matrices can be defined as an optimization problem, right? So we want to find a matrix such that once we multiply our matrix by another matrix, the result will be as close as possible to the identity matrix. So this is the definition of the problem of inversing matrices, but defined in the terms of optimization. Ensemble learning, how to find the proper set of parameters or weights for different models which we ensemble. So I already heard about quantum algorithms, quantum counterparts for some classical machine learning algorithms such as SVMs, generative adversarial networks, or even reinforcement learning. So it's important to see and to realize that we have a progress that is quite decent, I would say. So because I mentioned that the idea of quantum computing emerged in 80s of the 20th century, so it's almost 40 years ago. But for many years, the progress was relatively small, I would say. So there was a progress in developing better algorithms, but there was no significant progress in building quantum computers. But something happened about 4 years ago, because several companies started announcing that they were able to achieve some breakthroughs and build much better quantum computers than before. So, for example, in 2017, this D-Wave company from Canada announced that they have a quantum machine with more than 2,000 qubits for special purpose quantum annealing. IBM announced that they have a quantum computer with 50 qubits. 1 year later, Google announced that they have quantum computer with 72 qubits. 1 year later, Google announced that they achieved the quantum supremacy, right? And recently, D-Wave announced their advantage system with more than 5,000 qubits and new topology of connections. IonQ recently also announced that they have a quantum computer based on ion traps with 32 qubits with very low gate errors. So this is a progress that we should be aware of for sure, and I guess we can say that this is a decent progress, right? And later I will tell you why we think that. So we cannot be sure that this progress will not stop, and I think that it's still very likely that we'll have something like quantum winter, similarly as we had AI winter in the past. But there are also some theoretical justifications to expect that this progress will continue, and I will tell about it later. Another interesting progress was a progress not from the hardware part, but from the software part, because several research groups developed software development kits with access to quantum processors. So, for example, Project Q with IBM's quantum computer as a backend Qiskit, this is a framework developed by IBM. Forest, quantum computing framework developed by Rigetti, a startup from Berkeley. Strawberry Fields and Pendelane, developed by Xanadu. D-Wave Sleep, another framework for just preparing experiments for quantum annealing. TensorFlow Quantum, announced by Google quite recently, right? There are also some SDKs based on simulator, for example, Microsoft Quantum Development Kit with Q# programming language, and you can run experiments computation on a simulator of a real quantum computer. So how the future may look like. There's a famous quotation assigned to Abraham Lincoln and several other guys, that the best way to predict the future is to create it. So if you want to predict how the future may look like, the best way is to start working in the quantum computing field and start to shape this future, because there's a lot of work to do, and for sure you can contribute. But you should be aware that there are some obstacles on the road toward quantum supremacy. The coherence, right? So it's very difficult to isolate qubits from the environment. So, and in case of any interaction of qubits with the environment, we may get decoherence, and our quantum states may just collapse, may be broken. Error correction, right? So we may have physical qubits, but there might be some errors in measurements or computations performed by quantum gates. So a single physical qubit is not equivalent to a logical qubit. It's the same in case of classical bits. But now in case of error correction in classical computers, we are very advanced. And in case of quantum computers, probably there's still room for advancement, for some advances. Algorithms. There are still some obstacles in case of algorithms, because it's difficult to prove that quantum algorithms will be better than classical algorithms. And even for Shor's algorithm, we don't know, we cannot prove that the problem, the factorization problem, is not in a class of polynomial problems, right, which can be solved by the polynomial algorithm. We expect that it's not in this class, but we haven't proven it yet. At least we haven't published. There is no published proof. Yeah, so, and building some quantum gates is still challenging. It's still challenging, and I will also tell you later about it a bit. So since our quantum computers are still very noisy and there might be errors in computations, there are some ideas to just build frameworks which may take advantage of this noise, such that maybe we'll be able to still run some computations and achieve good results even for noisy quantum computers. So there is such an idea as NISQ, Noisy Intermediate Scale Quantum Circuits. And there is a Python framework developed by Google, as far as I remember, Circuit, which is a Python framework for creating, editing, and invoking such circuits. And this is a citation from the Google Quantum AI group. They said that they are developing a framework to implement a quantum neural network on near-term processors, so these noisy processors. We are interested in understanding what advantages may arise from generate massive superposition states during operation of that network. There are some other efforts from Google. So you probably heard about the paper published last year in Nature, Quantum Supremacy using a programmable superconducting processor. So basically, they've proven that they found a problem and showed that they can solve a certain problem on a quantum computer much faster than we can do that on even the best available supercomputer, right? And initially, the idea behind this problem, this approach, was published in 2018 or maybe even earlier. But in the paper from 2018, which was also published in Nature, they said that here we propose the task of sampling from the output distribution of random quantum circuits as a demonstration of quantum supremacy. And that was the idea behind this achievement. I also told you about the quantum error correction, and that physical qubits are not the same as logical qubits. But there are also some ideas how to build error correction codes. So, for example, let's assume that we have at most one qubit may suffer a bit flip. right? So then let's represent this pure state 0 as a state of 3 zeros, in fact, 3 pure state zeros. And the same for a pure state 1. And now when we do a measurement, and we know that in this case only one qubit may suffer a bit flip, then the result of the measurement should be 0, 0, 0 or 1, 1, 1. But if the result is different, but only one qubit, one value is flipped from 0 to 1 or from 1 to 0, then we can still easily get the correct result. But here we just needed three physical qubits to represent a single logical qubit, right? So can we do that better? Probably yes. So I told you about Peter Shor, who discovered or invented this factorization algorithm, but later in 1995, he also proved that quantum error correction codes exist. Right, and later another scientist, Aharonov and Michael Benor, and some other researchers working independently proved that these codes could theoretically push error rates close to 0. And later, Scott Aronson said that this was the central discovery in the 90s that convinced people that scalable quantum computing should be possible at all, that it's merely a staggering problem of engineering. So at least in theory, we know how to build these quantum error correction codes, or we know that at least they should exist, right? And in theory, we can push the error rates as close to 0 as we want. So there is a hope that we can build such good quantum computers. But as Aronson said, this is merely a staggering problem of engineering, right? So how to do that? So as you have seen, there is quite a decent progress in the last couple of years. But I also mentioned that another interesting difficulty is to prove that quantum algorithms will be better than classical. And I told you that even in case of the problem of factorizing large numbers, which may find applications in breaking cryptographic codes, it's difficult because we haven't proven that the factorization problem cannot be solved in polynomial time. And there is a similar example. There was something that's called recommendation problem, which for many years was believed to be also not solvable in polynomial time. And Scott Aronson gave a task to one of his gifted students, Ewing Tang, to prove that this problem cannot be solved on a classical computer in polynomial time. While in case of quantum computer, the polynomial time algorithm was already known. But this 18-year-old student proved or found a classical algorithm after many years. He found a classical algorithm solving this recommendation problem in polynomial time. And this algorithm was inspired by the quantum algorithm. So he just tried to understand where exactly is this quantum advantage, why there can be a polynomial time algorithm for a quantum computer, and why not for classical computer. He wanted to find it, and he haven't found it, but instead he found that the similar algorithm can be run in polynomial time on classical computer, right? So even if we cannot prove the advantage of quantum computers, then there's still hope that we'll be able to solve some classical problems better, or some computational problems on classical computers better, that will be just inspired by quantum algorithms. Or as Aronson said, maybe it's still possible that we'll find some new laws of physics, of quantum mechanics, that will just tell us that we cannot just build better quantum computers. So it's also still possible. So yeah, about building quantum computers, I already told you that several companies recently announced better and better quantum computers with better topologies of qubits, of connections between qubits, with more qubits. All right, so basically there are different approaches to build quantum computers. They may be computers based on ion traps, superconducting qubits, I guess that for many years this superconducting qubits approach was dominant, but now I heard that the ion traps approach is getting better and better, and probably the recent advancements were mostly in this approach based on ion traps. Another interesting example is this D-Waves machine, which is a quantum annealer. In fact, there are photonic qubits as well. There is an idea to build topological quantum computer. This is investigated by Microsoft and some researchers from Delft University. As far as I know, such a computer doesn't exist yet. There are some nice frameworks for learning how to code, how to write quantum programs. And in these frameworks, you can write your quantum code and run computations on quantum computers, on simulators of quantum computers. Penelane, it's a framework developed by Xanadu, another company from Canada. It was probably the first library for the quantum machine learning, so it was called the TensorFlow of quantum computing. But later, Google released TensorFlow Quantum, so now it's our TensorFlow for quantum computing. Qiskit, a very popular, probably the most popular framework developed by IBM. PyQL, developed by Rigetti. Project Q, developed at ETH Zurich. D-Wave Sleep, it's a framework available thanks to D-Wave, so we can run these quantum annealing computations. And most of the frameworks uses Python. So when you use some frameworks, then in most cases you just use Python. But recently I heard that Julia might be also a very good approach and very good programming language for quantum computing. And there is also a library called yao.jl, which is just based and written in Julia, and you can write quantum code in Julia. And yeah, I heard that it might be even better approach than Python in case of quantum computing. So we'll see. So the future is exciting. And now, what's next? So if you want to start working in this field, what can we do? There is an interesting initiative called QWorld. I already told you about it because my group, Q Poland, is a part of QWorld, and QMexico is also a part of QWorld. So QWorld is a global network of individuals, groups, and communities collaborating on education and implementation of quantum technologies and research activities. Right? So we have several channels. You are free to join us. We have also Slack channel where we have a few hundred researchers and quantum enthusiasts from many countries. We have right now 11 quantum cousins. So these Q cousins are just independent groups operating locally, as in your case in Mexico, in my case in Poland. But we just share our knowledge. That's why I'm also here. We collaborate, we develop educational materials together, and thanks to that, it will be easier for all of us to learn quantum computing and make some advancements in quantum computing, right? So in case of some countries such as United States, Canada, China, maybe United Kingdom, these are quite wealthy countries and they can just develop quantum computing technologies on their own. But in case of many other countries, it's very reasonable to collaborate and work together in this field. And for sure, thanks to that, we can just achieve more. If you are interested in quantum programming, we organize workshops based on materials called Bronze. So even currently, there's an open registration for the global workshop called Global Bronze Workshop. I guess that QMexico, as far as I know, QMexico also has already organized a similar workshop based on Bronze. So maybe some of you already participated in such a workshop. If not, then I strongly encourage you to participate. We also organize quantum hackathons. For example, QTurkey organized such a hackathon some time ago. There is a channel Q Women to just encourage women and girls to start working in the quantum computing field. A similar channel for juniors, for students from high schools, for our minorities, and for our minors. We have also Q Kitchen. Q Kitchen is a public repository for developing and sharing our educational projects, our code, and similar materials. So it's also open. There's repository is on GitLab, available on GitLab. So feel free to join and also contribute. Q University, it's our idea for running quantum computing semester and quantum computing courses at universities. We also train our mentors, our educators, who can later organize similar workshops, courses on quantum computing. So yeah, you can also participate in such trainings. Currently, we have this Keyword Challenge Autumn Edition, where we organize many workshops all over the world. So I remember there was a workshop in Mexico. Next week we'll have this global workshop. There will be also a similar workshop organized by Q Poland. Q Intern is another interesting initiative. If you want to work on an interesting research project and be supported, mentored by an experienced researcher, then you can participate in Q Intern next year. So this year we had the first edition. So experienced researchers from many countries, participants of Keyword, propose their interesting research topics. And we also gathered students, juniors who were interested in working on this research projects over the summer, and later they also presented the results of their work over 2 months, right? And they were just working on these topics and being mentored by senior researchers, so I believe that they learned a lot during only a couple of weeks. These are some interesting links, so you can follow the website of Keyword, you can follow our Facebook page, Twitter profile, you can join our community Slack and internal mailing list. We are also supported by Unitary Fund. So Unitary Fund is also a very interesting initiative. If you have an idea for an open source project in quantum computing, you can apply for a research grant. It's not a large grant, it's only $4,000 in cash, but anyway, it's still quite a decent support, especially for students. And the most important requirement is that it should be an open source project. But I strongly encourage you to work on open source project. There are many companies in the quantum computing business already, so these are just some examples. If you want to learn more, I encourage you to attend the webinars organized by Keyword. There's an interesting course on edX on quantum machine learning. And the lecturer was Peter Witek. I also recommend you some lectures prepared by him, which are available on YouTube. Here in Poland, we also organize meetings and webinars of Warsaw Quantum Computing Group. We also have our own YouTube channel where we publish the video recordings. You can join the Facebook groups such as Quantum Computing Now or Quantum AI. Quantum Information, Quantum Computer Scientists of the World Unite, probably the largest quantum computing group on Facebook. Facebook group of my group, also Quantum Computing Group. There are some interesting newsletters to which you can subscribe. For example, Quantum Computing Report. There are many online tutorials of Qiskit, PyQL, PennyLane, Swiss Quantum Hub, another newsletter. This time, this is a daily newsletter, so you can receive every day some news from the quantum world. There are also some similar initiatives such as Qreka, where there are they also organize courses, workshops on quantum programming and quantum computing. I think I can also encourage you to and recommend you to follow their websites and their social media and to stay up to date. That's all from my side. So I thank you for your attention. It looks that we still have some time for questions, so I'll be happy to answer. Thank you.
Okay, nice. Very good. Hey, Pawl, I enjoyed really your talk. It was very nice. First of all, I would like to say thank you on behalf of Mexico. The talk was very complete.
Thank you.
We are going to start with some questions, right? It's good?
Mm-hmm.
Yeah?
Yeah,
Okay,
sure.
but okay, I would like to know if there is someone from Mexico, QMexico, who wants to ask something. Oh, okay. So first, hello everyone. This kind of new computation is going to need new structures, like new stack or new binary tree. some like quantum 3.
Mhm.
Yeah, that is a question. First
That is
one.
okay. I can try to answer. So I agree, and I already told you that there are some quantum counterparts to some machine learning algorithms. For example, there are quantum neural networks or quantum reinforcement learning algorithms, and in fact, quantum neural networks are a bit different structure than classical neural networks, of course, right? So indeed, we may need some other data structures, such as quantum trees, probably as well. I'm not sure. I think that I probably haven't heard about quantum decision trees or quantum XGBoost, quantum light GBM. Maybe there might be some such approaches as well. But yes, that's true. That there might be such quantum new quantum structures, new data structures, new structures for processing data based on quantum computing. Indeed.
Okay, good. Um, okay, other one. What makes a programming language better than another one for
Mhm.
quantum computing?
Yes. So I mentioned that most of these quantum programming frameworks are based on Python. But um, Python is if you have some experience with Python, then you might know that Python is not the best language for parallel computations, right? And here, in case of quantum computing, um, you often so even if you want to run some simulations of a quantum computer, then it's good to parallelize some computations, and you also have to run
Okay.
some operations on matrices, for example, right? And if you run operations on matrices, then okay, Python have some nice libraries for that. But I heard that Julia is also a very good programming language, especially optimized for parallel computations. So that's why, because of the libraries for operations, running operations on matrices, vectors, tensors. That I guess that this is one of the reasons why Python is such popular, right? So this is an interpreted language uh, which have which has many good scientific libraries for scientific computations. And here, all the computations in quantum computing are quite an advanced mathematics, as you have seen, right? And in many cases, indeed, you have to just multiply some matrices, for example, right? So Python has some good libraries for that, but I heard that Julia might be or is even better than Python for especially for this kind of computations.
Okay, but there are different groups working on to develop more quantum programming language, right? For example,
Um,
Silk, yeah, in
yes,
French, I think so.
yes. So there's, for example, even Microsoft developed this Q Sharp, right? And
Q
regarding,
sharp, right?
yeah, you said about this CRQ, right? So I guess that you meant this framework developed by Google, I guess, for CRQ. I guess this is a Python framework, right, for NISQ. I'm not sure if there is a separate programming language, because I see that there's a Python framework, but maybe you had something else in mind, because there's also something like SealQ, I guess, right? So probably that is something that you had in mind. So there are such ideas. So I also mentioned about the Q Sharp language developed by Microsoft, right? So
Okay.
there are such approaches, and as you can see, we have many different approaches to build quantum programming frameworks. We have many different approaches to build quantum computers, and I think that it's good, right? Because later we'll just after some time, after many years, probably it will turn out that some approaches are better for some reasons, for some applications, and some approaches are worse, right? So now it's a perfect time to explore different opportunities, and that's why it's also good to develop some new programming languages. I guess that Microsoft also wanted to have a programming language that would be compatible with the Visual Studio framework,
Yeah.
which can be used, right, because they developed the whole quantum development kit, right? So there is a development kit, there is an integrated development environment, there is a programming language, there is a quantum compiler, right? So this is the whole environment. So that's why they wanted to have it integrated with the tools which they use for classical computers, because, as I mentioned, Microsoft's approach is based on just the endeavor to build this topological quantum computer. But before they will do that, if they even if they do that, then before that they will have to run computations on simulators, so on classical computers, right? So it's not something strange that they wanted to have a framework which will be compatible with some other frameworks which they have for classical computers, right? So Python there is also something like Iron Python in case of the .NET framework for Microsoft, but it's not that popular. So I guess that they also wanted to build something new and more optimized for the quantum computations, I guess.
Yeah. Okay. Thank you.
Hi.
One more.
Can I ask a question?
Sure.
Sure.
This is Sandra from QMexico. First of all, thank you so much for your talk. It was a nice overview of the world ecosystem. So coming back to the application that you showed for vehicle routing, you
Yeah.
mentioned that the number of logical variables that you have, it was somewhere in the order of 1,000 something. So
Yes.
that's really close to the number of qubits on the QPU that you mentioned you use for
Yeah.
solving this problem. So
Yes.
were you actually able to embed the full size of your problem into the Chimera graph, or did you use some sort of like
So
optimization code for embedding?
First of all, that was the experiment conducted by researchers from D-Wave. So to be honest, I'm not sure how exactly they did that. So I know that they run it on this D-Wave 2x QPU. So I guess that they had this Chimera architecture with more than 2,000 qubits. But to be honest, I'm not sure how exactly they did it. So you can, if you're interested, please check this paper. So this is a very nice publication in which they explained this experiment. And as far as I remember, they also probably explained how exactly these experiments were conducted on D-Wave's machine. I'm not I don't remember.
I see. Thank you.
All right, thank you.
Thank you, Andrea. Okay, one more. What would you do with a quantum computer that fully works as we want them to? One more. What would you like to know about the world using a quantum computer? We have two
Okay, so
more.
let's go back to the first question. Can you repeat the first question?
Okay. Sure. Yeah. What would you do with a quantum computer that fully works as we want them to?
What I would like to do with the quantum computer, right? If assuming
Yeah,
that
I think so.
it will work as we want them to do. So I personally work in the transportation field. That's why I also give you this example of traffic flow optimization and logistic optimization, because these are the research problems on which I personally work since 2009. Yeah, I started working on these problems in transportation in 2009, and I also apply artificial intelligence and machine learning to solve some optimization problems in transportation. So for sure, in my case, that would be the application of quantum computer, the most interesting for me. But if you ask more generally, I guess that I also mentioned about some possible applications here, and discovering new materials, new drugs. That would be something in my opinion, very interesting. I even heard that there were some research groups trying to develop algorithms for designing drugs and maybe even vaccine for COVID-19. So of
Yeah.
course, our quantum computers are not as powerful, but for sure. So when we just deal with new materials, new drugs, this is just a chemistry, right? And the chemistry is governed by the rules of quantum mechanics. And for sure, I strongly believe that quantum computers may bring an advantage in this field, because currently, as far as I know, researchers have to run really time-demanding computations in order to simulate how different chemical substances react or may react in such a scale, right? I don't have experience with that. That's why probably it will not be the primary area of application for me, because I just don't feel that I have enough expertise in this area at the moment, at least. But when we just look at the whole society, I guess that it would be one of the most interesting, important applications to just discover new drugs, discover new materials. And also, I mentioned that there might be many applications, potentially applications in machine learning, artificial intelligence, in solving the combinatorial optimization problems. And we know how important currently AI is becoming, and already has become, right? So it's super important. It may find
Yeah.
applications in many fields. So the question is whether machine learning can be really enhanced by quantum computing, right? Because currently we have some GPUs, TPUs, right, which are used to just run some computations. It's possible that in the future some computations in machine learning will be also run on quantum computers, but we cannot be sure. But I'm also afraid, and here I said that I'm really afraid, is that one of the first applications of quantum computers might be to break this current cryptography and classical cryptography algorithms. I even heard recently that we'll wait for quantum computers, for a real and powerful quantum computers, for many years, not because we don't know how to build them, but because we are not ready for that, right? Because if such quantum computers will appear at some point, then someone may want to use them to break cryptographic codes which are currently used over the internet, which might be very damaging, right? So,
Yeah.
that's why you should also be aware that there might be very good applications, but also very bad. But it's the same with everything, right? So you can use a hammer um, to just build something, but you can also do a harm to someone, right? So everything depends on the
So
person using a given tool. Yeah, but in my case, it would be probably optimization of transport logistics, because this is the area in which I'm working um, since 2009.
yeah.
The second
Thank
question,
you, Paul.
or I'm not sure if you
The
still have time,
second.
probably not. Yeah, there was a
No,
second
I
question.
think you. Yeah, yeah. Second one is, what would you like to know about the world using a quantum computer?
What I would like to know
The
uh,
world
about the world,
using, yeah,
about the
using a
world.
quantum computer.
Uh, it's hard to say. So I guess that this is a question about some possible discoveries, right? Which we can achieve using quantum computing, right? I'm not sure if I understand this question correctly, but yeah. So I guess that.
Yeah.
So I think that once again I will say this. I will cite Scott Aronson, who said that one of the most interesting outcomes of this whole progress in quantum computing might be to discover some new laws of quantum mechanics, some new laws which just
Yeah.
govern our world, because we cannot say that we know everything about quantum mechanics, right? There are still many things
Yeah.
we don't know and we don't understand. And I believe that working on quantum computing may help us do some new advancements in our understanding, in our basic pure knowledge about the world and quantum mechanics.
Yeah, yeah. Okay, but for me, it's complete. You first answered where you discuss more about, for example, the vaccine against the COVID-19 or something like
Yeah.
that. I think that is very useful for the humanity, at least, right? Okay,
Mhm.
so Powell, really was great. Thank you to stay with us in this talk. Thank you to be here with in QMexico, and yeah, I think with this we can finish the talk, and we would
Okay.
like to discuss another occasion, right?
All right. Thank you very much. Thanks for having me here. It was a pleasure, and take care. I hope to see many of you uh, on Keywords meetings, and there might be also some other opportunities in the future in our quantum world.
Thank you. Okay, perfect.
Yeah.
Thank you. Okay, bye bye.
Bye bye.